So this is my pet project where I upload an image and ask Gemini 3 Flash preview model to generate some hashtags relevant to it. And then I ask the same model to use the hashtag and the Google search tool to find an obscure fact, which it did. So my demo is to pass this text, right? This text to the TTS model to return a WAV file or a WAV data, so that the data can be played in an HTML audio player element. So I have three use cases. The first case is to ask the model to generate the content synchronously, to have the inline data ready, and then the cloud function convert the data from L60 mean type to WAV mean type, and do some additional work to construct the Base64 encoded string and pass the entire string back to the front end. That's the first use case. The second use case is to generate the content in streaming mode, and the chunk is sent back to the client side to be collected in an array, and then the whole array buffer is used to create a block URI, and that block URI is assigned to the source of the HTML audio player to play the audio. And the last case is a little harder and more efficient, or it has better user experience. Similarly, the content is generated in streams, and then each chunk is sent to the client side, and the Angular create an audio context using the browser web audio API, so that the audio can be played immediately when the first chunk arrives to the client side, so the user can listen to the text sooner, rather than waiting for every chunk is in the client side before it is concatenated into a buffer and being played using the HTML audio player element. So we will try these demo next. So this is the first use case where the backend generate the content synchronously and then convert the L16 data into Base64 WAV data, and then the entire string is sent back to the client side to render the HTML audio player. So
a surprising interconnection between these technologies is that Firebase was originally an online chat tool called Involve before it.
And in the dev tools, we can check the response of the cloud function. The result is a Base64 string, right? And this is, so it's data, the mean type is audio/wave, Base64, and then some human unreadable text. And let's see. This is the, yep, and then this, well, this, and then this data, and then this data string is assigned to the source of the player element. So this is the first use case. The second use case is to ask the Firebase cloud function to stream the result. Like the function sent chunks to the client side, the Angular application store all the parts in an array, and then that array is converted to a block URL, and the block URL becomes the source of the HTML audio player. So this is the blob URL with blob prefix and then the URL like http / localhost 42,000 and something. The response, okay, definitely not a base64 string. It looks like buffer that contains human unreadable characters. We can also play this audio, and you should notice the tone is different. The person reads this paragraph in a happier tone instead of the dark tone in the previous use case.
A surprising interconnection between these technologies is that Firebase was originally an online chat tool called Involve before its founders noticed it.
So this is use case number 2, and both use case number 1 and number 2 have the same problem. Like we have to wait for the entire audio to be concatenated and to do some processing and assign the data to the source of the HTML audio player element to play. So we have to wait a short period of time before this element to appear, and we click the play button to play the audio and adjust the playback speed to 1.75 or to change the volume or to pause and to resume it. So the last use case is to click the
A surprising interconnection between these technologies is that Firebase was originally an online chat tool called Involve before its founders noticed developers were using it to sync non-chat application data, leading to the serverless powerhouse it is today.
So we noticed the difference, right? After I click this button, before I could finish my sentence, the speaker started to read the paragraph, and the playback rate was randomly chosen. It was fixed to 1.22, and then I was not able to change it again using any audio control, but that was okay. I wanted to show the difference between streaming to client side, wait for all the parts to arrive to convert to blob URL to appending the stream to the audio context, and the audio context started playing immediately. So I have shown all the use cases, and I'm ready to show the code in the cloud function. To be honest, the backend code is easier to implement than the front-end code, so I want to do a code walkthrough in the backend first, and then in the front end. So in here, I have a group called text to audio to group the TTS cloud function, and the index.ts file is under text to audio folder. So in this file, I have one cloud function called read fact to read the obscure fact that the front end passes to the cloud function. So in here, data is a string, and acceptsStreaming is from the Firebase to tell whether or not the client side supports streaming results or not. So if acceptsStreaming is true and response is defined, so I call the read fact function stream to stream to do streaming and send the chunks to the client side. If acceptsStreaming is false or response is false, then I call read fact function that generate the content synchronously and return the base64 data string to the client side. So yeah. So let's go through the readFact function. So it calls the helper function to validate the environment variable to make sure the location, the TTS model name, and the project ID are available. And the function return gen AI options object and the model name back to the readFact function. And then we call the generate audio function to return the base64 encoded string. So in here, the content is the dark faded tone and the text. So the dark faded tone is to instruct the model to talk like Darth Vader with a deep voice and heavy breathing, and to instruct the model to read the text below exactly once. And then I call the generate content method to obtain the entire inline data. So the Corey voice config is an instance of generate content config. The output is an audio. It's an audio string, and use the pre-built voice config with the voice name Corey. And then I get a generate content response back. I pass the response to the get base64 data URL, get the inline data, and get the raw data and mean type from the inline data. If either the raw data or the mean type does not exist, an error is thrown. Otherwise both the raw data and the mean type are passed to the helper function encode base64 string to construct the base64 data URL. So in here, the L16 raw data is converted to WAV, and then the WAV button is converted to a base64 string, and then I prepend data colon audio slash WAV semicolon base64 colon to the base64 data to construct the base64 data URL and return it to the client side. So next, I want to show how to send chunks to the client side to play the audio in an HTML audio player. It's done inside the readFact function stream function. So the function takes a text and a callable response. So this function is very similar to readFact function, except it invokes the generate audio stream function instead of the generate audio function. So this function awaits AI.models.generate content stream to get some chunks back. And then I for await chunks to get a chunk back. And then I attempt to get the inline data from the chunk. And then extract the raw data and the mean type from the inline data. And I use the first mean type to construct the wave options. So when both raw data and mean type are available, I increment the raw data length, and then I convert the raw data into a base64 buffer and send the buffer to the client side. So when all the chunks are processed and sent to the client side, I use the raw data length and the wave options to construct a wave header, and then I spread the wave header to get an array of bytes back, and then this header is sent back to the client side, and this header will be inserted at the beginning of the of the audio buffer before the entire thing is converted into a blob URL and assigned to the source of the HTML audio player to play the audio. So this concludes all the changes in Firebase. So next I will show the code changes in the Angular application. So the text-to-speech component has 3 buttons. Let's open the template. So the first button generates the audio synchronously in the backend. So the backend returns an encoded Base64 data URL to the client to play the audio in the audio player element. So the second button triggers the backend to send chunks to the client side. So the client has a buffer array to gather all the audio parts and the wave header. After everything is available, the Angular application converts the buffer array into a blob URL, and the audio player element plays the URL instead. So the third button uses the audio context of the web audio API. So when the first chunk arrives to the client side, the client start playing the audio, so the user doesn't have to wait so long to hear the speech. So when the button in the text-to-speech component is clicked, the generated speech output emits a value of type generate speech mode, and the caller receives this mode and determine which method to call to get the audio data back from the cloud function. So the text-to-speech component is in the Oscure fat component. So the generate speech custom event, when it happens, causes the Oscure fat component to call the generate speech method. So when mode is either sync or stream, the speech surface is needed to call the cloud function to get either a blob URL or an encoded Base64 data URL. And then the generate speech helper cleared the error signal, set the loading signal to true, so the button is disabled, and we see a spinner. So when the URI comes back, the URI is set to the URL signal, so the audio player is displayed, and user can click the controls to play or pause audio or to adjust the playback rate. So let's go to the speech surface. So config surface is a surface that store functions, Firebase app, and a remote config, so that they can be referenced in different places in the entire application. So the generate audio creates an HTTPS callable function, and then I pass the text to the read fact function callable function to get the audio URI back, and the audio URI is the encoded Base64 data URL, and this URI is the source of the audio player element. So the generate audio blob URL uses the generate audio stream method to get the stream and the data back. Data is a promise that return the wave header in an array of bytes. So the generate audio stream accept a text, and then I also create an HTTPS callable function, and I call read fact function dot stream and pass in the text. So back to generate audio block URL method, I await the stream to get the audio chunk, So when the audio chunk has a data property, I convert the data to an uint8 array and append the array to the audio parts array. And when all the arrays are pushed to the audio parts array, I await data promise to get the wave header. And when the wave header is defined and it is a non-empty array, I insert this wave header to the beginning of the audio parts array, and I pass this array to a helper function to create the Blob URL. So in here, I mentioned the content type is audio wave, and I use URL dot create object URL to create a Blob URL from a buffer array or from an array of blob parts. So similarly, this method return a string, and I can assign this string to the source of the audio player to play the speech. So last, we will walk through the playstream method to see how the AudioContext start playing the speech when the first chunk arrives from the backend. So this. So the stop all method is to stop playing all the source nodes in this active sources list. To free up the resource, reset the array and the next start time. We use the generate audio stream method of the speech service to get the promise and the stream. And I for await a stream to get the audio chunks. And for each audio chunk, I pass audio chunk.data to the process chunk method. I await data, but I don't care about the returned wave header, so I ignore it. And let's go to the process chunk method. So this method, this some magic to convert the raw data to an array of flow 32 values. And then I create a buffer with one channel. The length is the length of the flow 32 data array. The sample rate is 24,000 megahertz. And then I copy the data to the only channel. And then I call this method to create a source node. Right, assign the audio buffer to the source buffer, and I connect the source node to the destination of the audio context. And I used the active source list to keep track of the source. So when the source node is done playing, it is removed from the active sources list and return the source. So when the tab is closed, while the speech is playing, the ng on the short lifecycle hook makes sure to stop all the source nodes, disconnect all the source nodes, clear the active sources list, and reset the next start time to 0. Okay. And then I go back to the process chunk method. So each source node has the same playback rate. So this playback rate is a random value. So the voice config can speak fastest or slow, like randomly, and set the start time of the source node, and do some map to calculate the actual duration and update the next start time. So when the chunk arrives to the client side, the audio content make sure it is processed, and we can listen to the audio data of each chunk. So and this stream speech with web audio is a helper function to set the loading signal to true, so all the buttons are disabled, and the web audio API button has a spinner, and yeah, I'll wait the function to listen to the entire speech, and in the finally clause, the loading signal is reset to false, so all the buttons are enabled, and we can click them to play to generate from text to speech using the Gemini 2.5 Flash TTS model. So this is the code walkthrough of the Angular application, and I hope you enjoy this tutorial, and you may able to find some use cases to use the Gemini 2.5 Flash TTS model to generate speech from text in your web application to, I don't know, integrate AI capabilities for your project or for your scenario. So I hope you have a good day, and I'll see you later. Bye-bye.